All right, let's dive straight into part 2 of our dielectric and insulation strength explainer. In the first part, we laid all the groundwork for how we actually prove a transformer's insulation can hold up against extreme electrical stress. But today, we are exposing a hidden danger. We're talking about a seemingly simple oversight that can literally physically hurt you and completely ruin your equipment if you're not paying attention.
So, just as a super quick refresher on our standard testing sequence, step 1 is always insulation resistance testing, which acts as our non-destructive baseline. Step 2 is the applied voltage test, and that verifies the outside gap between the winding and the tank. And finally, step 3, the induced voltage test, checks the interturn insulation within the winding itself. That is the safe, standard sequence we follow. But before you even think about starting that sequence, there is an absolute non-negotiable rule in standard maintenance procedures. Never perform electrical tests of any kind on a transformer under vacuum. It's that simple. Skipping this check invites a completely invisible hazard. Now, you might be wondering, why is this rule so incredibly strict? Well, when a transformer is under vacuum, meaning it's been totally stripped of its insulating oil or atmospheric air, its dielectric strength is absolutely decimated. That gap simply cannot hold back the voltage anymore. A catastrophic internal flashover can happen at a shockingly low 250 volts. To put that into perspective, that is roughly your standard household voltage. Yet inside a vacuumed tank, that everyday voltage is enough to cause a massive destructive internal arc. Crazy, right? Honestly, this extreme vulnerability brilliantly illustrates exactly why we do these withstand tests in the first place. We are not just checking to see if it survives everyday normal operational conditions. We are intentionally subjecting the equipment to deliberate, extreme overvoltage. It's kind of like load testing a brand new bridge. You don't test it with normal cars. You park weights on it that are far heavier than regular traffic. We do this to definitively prove the transformer will survive a once-in-a-lifetime extreme event, like a massive lightning strike or a huge switching surge. Let me tell you about a real-world near miss to show you how this plays out. So, a high-potential test is scheduled on a recently dried-out transformer unit. Literally, right before connecting the high-voltage set, a sharp-eyed technician happens to check the vacuum gauge. And guess what? It's reading negative. The unit was actually still under vacuum from the drying process. So they halt the whole shebang. They wait for the tank to fully refill with oil and equalize back to atmospheric pressure. By simply reading that one gauge, they safely conducted the test and completely avoided a catastrophic flashover at a fraction of the intended test voltage. Okay, pop quiz time. Let's make sure this protocol is fully internalized before you step out into the field. Imagine you walk up to a unit. Cables are prepped and ready to go. But right before you begin your high pot test, you notice the pressure gauge reads in the vacuum zone. What's your next move? You stop immediately. No questions asked. You absolutely must confirm the oil fill and ensure the tank is at atmospheric pressure first. Verifying the physical, mechanical, and atmospheric safety must always, without exception, come way before testing any electrical function. Keep that rule firmly in your back pocket, and you are golden to sequence your dielectric tests safely and confidently. But actually, this leaves us with a really interesting question to ponder for our next explainer. Once a transformer proves it can take a massive hit like a lightning strike, how do we measure the everyday hidden financial cost of just keeping that massive thing energized and sitting idle on the grid? Think about that for a bit. We are going to tackle efficiency and loss assessments next time. See you then.